everybody, from your favorite artist electronics, Mr. Guitar here. I have a new component that I never had before. I only read about it, and it's called this TVS diodes, and is having this special marking. Is designed to protect against EFT, electrically fast transients, and ESD, electrostatic discharge. This ESD is more important to me than anything else, actually, and that's why I bought a couple of values: 5 volts, 9 volts, 12, 20, 100, and 170. Actually, this last one, 170, I needed actually like 240 volts actually, but the seller didn't have that value, so I took these values that he had. I'm not completely sure if what I'm having here will even work directly to 240 volts. We will see in the future, but for now it's just an interesting component. As you can see here, I'm having this little CA marking. It means alternative current, or it means bidirectional. You can see it here, A and CA, and they all have this TVS diodes. They all have this special marking, A for unidirectional. It means like when it's looking exactly like a simple diode, not like this one that is here, and this CA that is this symbol that you are seeing it here. Actually, the A version, the first one, is having a polarity line on the diode there, while this CA bidirectional one is having absolutely no markings, no polarity markings on the diode. It's just black thing. This is the circuit that I figured out how to test this diode. I had to look everywhere actually. It turns out that these diodes that I'm having here, let me show you how they are looking here inside. So these are the values that you're seeing here, 170 there. This one, so I tested already a couple of them. This is the 5 volts one. Yeah, you can see 5 volts, and also this 9 volts one here. I will put it to the test as well. Why I'm testing this very small values? Because it's easy to test them comparative with larger values. So that's why I originally bought them. I'm not completely sure if I will ever use them anywhere else, but we will see. This is how they are looking, and these are the actual sizes of them, as you can see. I managed to damage this one, to rip off one of its legs, and right now the circuit is exactly like you're seeing it here. So I'm having I have two modalities of testing this very special TVS diode. This is a tester for 5 volts, but you can use whatever value, and you will see when I will test this 9 volts one. It is the same thing. It is with alternative current and with direct continuous current. And so this is 20 volts AC, it says there, or DC, but very fast. Well, fast enough. You will see in a second how I'm proceeding. So here is a point, either alternative or direct current, and the negative here, and here is the diode, and here is the resistor, 100 ohms, 5 watts is this one here, and there is the diode, and I linked it. This is the negative rail passing through the diode, as you can see here, and through this resistor, and to the positive rail, which is here. And that's it. That's the entire circuit. And if I'm using alternative, the polarities doesn't matter, but it's the same trajectory of the current. And here, these arrows, this arrow and this arrow, are the oscilloscope probe, where I put my probe. So I linked here to the negative directly, as you can see there, and this is the other probe that I linked it there in that junction. And that's it. All right, so this is the normal functionality of this TVS diode, the 5 volts one, this one. Right now, my power supply is set to 5 volts there, and my oscilloscope is reading 5 volts over that junction. V minimum as well as 4.97, because V max and V minimum is for waveform, pulsing or oscillating voltages, while right now it is constant and is reading both of them. But the most important one is this V max, my point of reference all the time. So while the voltage is equal with the value of the diode that I'm using there, or less than its value, no power is consumed. As you can see probably here, no power milliamps, or if they are absolutely negligible. If I'm putting my fingers and test for heating, nothing is heating up, and I'm keeping them for a couple of minutes now, running like this. In this normal mode, this is the normal mode, when it's the same value, when that voltage is not exceeding the diode voltage, and when it's less or equal, it's fine. Let's put it to 3 volts right now, just because I can. And here as well, so now is even less power consumed by everything, and my oscilloscope is showing me exactly that value of 3 volts, and absolutely nothing is heating up, is functioning normally right now. This is the normal functionality of this component. All right. Now let's see, because is doing this thing because it's not powered and it's catching some interference probably from this breadboard. But when I will connect, so I will have to touch there, and when I will touch it, I will obtain a result. This is the power that I will use. Actually, because this is a 5 volt, I can use less voltage here. So I can use, yes, 8.5 volts. Okay. So when I'm touching here, then you will want to look there. This two on the top, you want to look, and it's 7.26 and 7.06. Unfortunately, so this is the 5 volt one. Unfortunately, it's not 5 volts. It's showing me that 7 volts. So this is the idea of this TVS diode. When it's catching something, a voltage that is over its rating, it is clipping the voltage to 5 volts pretty much. It's forcing everything to 5 volts, but is dissipating the rest of the power on this resistor. So it is doing its job there, but the rest of the power is dissipated on this resistor there. If it was by itself, it was making a short circuit, and all the power was over this component if I was linking it directly without this resistor, and having too much power on it was getting extremely hot, very hot. I did made some mistakes, but I managed not to damage the component. So I took another one in the idea that this highly experimented diode that I'm having here might be might be damaged in some way because of those experiments I did before. But it turns out the second one gave me exactly the same results like the first one. So although I did some very brutal experiments with one, it did survive. Very interesting, very interesting thing is that these pins, as you can see, I soldered these long pins here, and they desoldered from that heat. They desoldered, and they actually made a little bit of like a spring. They departed from the component, the leg, one of those legs. So the solder got melted, literally, liquid, and the pin got out several times. I actually did a couple of times this experiment. I connected this when I was connecting this power here, and keeping it for 2 or 3 seconds. It got extremely hot, but not in this configuration. In other configurations, when it was more direct, when all the power was on the component itself. In this configuration that is right now here, after I figure it out, all the power is falling onto this resistor, and a little bit of power on that component as well. That's why I have to move a little bit more faster. Not to stay too much in contact, because some power will fall over this component and it will overheat it, and it will not damage it, but it will overheat it. This TVS diode is made to catch extreme voltage in a fraction of a second. Like I read already here, it is designed to protect very short time duration, like microseconds, not even milliseconds, but microseconds or nanoseconds, to catch very high spikes, like the EFT spikes or ESD spikes. So those are extremely fast. What I'm doing here is very slow, very long time from the perspective of that diode. So, but it is resisting. It is, doing its job. I'm still getting some result. It's a protection diode. What it's doing is protecting the circuit, but for very short periods of time. That's the idea. And right now, like I tested it with 8.6 volts because I tested everything already, and I know. And right now, let's go higher in voltage. Let's say this. 11, okay, 11 volts. It doesn't matter how exact I'm there. The result is the same. So when I'm touching here, I'm getting that 7.36. It should have been 5 volts, but is a little bit off. And the same goes for this 9 volts one. Is a little bit off, but it's good enough. And let's go crazy. Let's go to 20 volts there. You see? And I'll do it again. Now the power, yeah, you see, 7 volts. Sorry, no. So it is clipping to 7 volts again. Actually, let me show you. Yeah, it's doing this. You see, when I'm making the contact is 130 milliamps there. So it's a lot of power dissipated, mostly over this resistor, but on this diode is almost nothing. And let's go even crazy. I will go to the maximum. This is the maximum, 31.8, 32 volts. And let me make the contact here. Yeah, you see, 776. And let me show you this, 240. So the resistor is starting to warm up. But I'm doing this very short test. 1 or 2 seconds, and it's good enough, I'm touching that point there. So this is made, what I did here, I did it with DC voltage. Exactly the same result I'm getting from AC voltage. Yes, I stopped the power supply and I disconnected it from the board, and now my my oscilloscope is behaving correctly. All right, so right now I'm having 10 volts alternative. Now we'll make the connections. There it is. So Vmax is 7, and voltage peak to peak is 12 volts. Okay, so it's set to 20 volts, and now when I'm plugging it in, I'm getting this, as you can see there. This is probably the clipping of the waveform, and I have to move fast, not to leave. It's very warm towards hot. So this is how you are testing it in these two modes, with alternative current and with continuous current. And it is showing that it is clipping it at that 7 volts Vmax. Let me show you again very quickly. So yeah, 7.8 and negative 8. So it is reading both sinusoidal waves, both polarities. That's it with the alternative test here. As you can see, it is doing the same. I'm getting the exact same response for alternative, the exact same reading, especially here on Vmax, that 7 volts, and also here negative 8. In this case, instead of 5, it should have been 5 and negative 5. The clipping, you know, so it is doing the job. This my oscilloscope is reading correctly that sinusoid, that alternative waveform. But I do prefer my direct current test is more safer, and is saying the same story, exactly the same story, saying it like the alternative. But if you have a transformer, plug in the output of the transformer, and for very short time test everything like I'm having it here. And also you need an oscilloscope or a multimeter, and you can read the values. And if you can read something, even if it's a little bit off, like I'm having it in this example, this should have been read 5 and is reading 7, it's good enough, you know. Next experiment, I will take this 5 volts out and I will put them aside, because it's quite difficult to know which is which. They don't have 5 volts CA marking on them. They have some weird lettering, and it's very, yeah, it's not good. Let me take out the 9 volts one. So I already prepared it last night when I was doing the testing. And let me setting it here. Very nice, okay. And let me power up my power supply there. I have to set up the voltage to, if I remember correctly, this was around 11 instead of 9. So it will be 13 like that. I'll put this, I'll connect this one, the positive here. And I'm getting that weird noise, but now when I'm making the contact, I'm getting, you see, plus 10, plus 11, 10.9, 11. So, okay, so this is for 13 volts. Let's do it for 20 volts like before. It's a lot of power dissipation, actually. And as you can see, it's plus 10, 11 there. And actually it's less power dissipation, because it's a little bit less power dissipation over that resistor. So let me show you again. It's yeah, 11.4 Vmax. You are keeping an eye here in this for this Vmax, and let's set it up to the maximum 31.8, 11.8, and here is okay. So this is the 9 volts one. Instead of 9, it clipped at 11, but it's good enough. I mean, it is doing its job, and this test that I'm having here is proving the functionality and that this component is good or bad. And yeah, that's it pretty much. You can use bigger wattage is better. If you have 100 ohms at 10 watts or 15 or 20 watts or 50 watts, it's better. You know, less wattage is not good. It will heat up very quickly, and you can burn the resistor if you are doing excessive testing. But if you are doing a very short test, it's good enough. You know, like one or 2 watts, but very short test, and read very quickly the display that you have there, the results. If you get some values very close to the actual designation of your diode, like I'm having here, instead of 5 I got 7, instead of 9 I got 11, and it's very close to the marking of these diodes, and it's good enough. You know, the diode is good, and you read its value pretty much, minus 1 or 2 volts tolerance, let's say, you know. Right, this is it for this very experimental component that I will probably never use. I took it for curiosity. I was very curious about it, and I'm very curious if I can actually use it in my future circuits as a protection diode. That's the only reason I bought it, for protection, more protection to my circuits pretty much. And yeah, I hope it is helping someone, and that's it. Bye bye from your favorite artist electronist, Mr. Q12 here. Bye bye.